Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have seen the concept of programming for time delays. The link of the previous video is available in the description box. Please check it. In that video, we have seen the concept of programming the timer in mode 1 and mode 2. For that purpose, we have seen some steps. The first step is load the T-mode register. By loading the values in T-mode register, we can select the timer in mode 1 or mode 2. Okay. The next step is load the TL and TH registers with initial clock values. By loading the TL and TH registers, we can obtain the proper time delay. The next step is start the timer. Next step, start the timer means if we use the timer 1, then we can start the timer by setting the TR1 bit. If we use the timer 0, then we can start the timer 0 by setting the TR0 bit. The next is observe the timer flag TF. In case of timer 1, the timer flag is TF1. In case of timer 0, the timer flag is TF0. Okay, then if this timer flag is set, then stop the timer by resetting the TR1 bit or the TR0 bit. Okay, then the clear timer for next round and go back to step second. I hope you all remember these things. In that video we have also seen some concept regarding to the loading values in T mode and TH and TL register. In that video, we have also seen one program that assuming that XTAL equal to 11.0592 MHz, write the program to generate a square wave of 2 kHz frequency on pin P2.2. That means this is the program for the generation of square wave on the port pin P2.2. Suppose this is the P2.2 pin and on this pin we have to generate this square wave. This is the square wave. This square wave has on time and off time, and here we consider the 50% duty cycle. That means on time is equal to the off time. This is known as the 50% duty cycle. Okay, I hope you all remember this concept. The solution of this program, first of all we have to calculate the time delay for the generation of this square wave. Okay, here we have the frequency 2 kilohertz. Then from this frequency we can generate or we can find the period, as we know that t is equal to 1 upon f. Hence the period of the square wave is 1 upon 2 kilohertz. It gives us the answer 500 microsecond is the period of this square wave. Okay, now let us consider that the duty cycle of the square wave is 50%. That means if this is a square wave of 50% duty cycle, then on time is equal to the off time. Hence the on time is 215 microsecond. Similarly the off time is 250 microsecond. Okay, then we have XTAL equal to 11.0592 MHz. That is the clock period is 1.085 microsecond. This calculation is already seen in the previous video. Okay, I hope you all remember this calculation. Hence, to obtain the number of clock pulses, we have to divide 250 microsecond by 1.085 microsecond. After this divide operation, we get the answer as 230 clock pulses. Okay, hence now we have to find the values for TH and TL by subtracting this 230 value from the maximum timer value FFF minus 230. But FFF is hexadecimal and 230 is decimal. Hence we have to convert this FFFF into decimal, and its decimal equivalent is 65,536 we have to subtract these clock pulses from this, and we get the answer 65,076. Okay, this is the decimal value. Convert it into the hexadecimal. Its equivalent hexadecimal is FF1A. Here, the lower byte is stored in TL and the higher byte is stored in TH. That means TL contains 1A and TH contains FFA. Okay, that means we we find the values for TL and TH as TL equal to 1A and TH equal to FFA. Here is this is the assembly language program for the generation of the square wave on the port pin P2.2. Okay, hence the instructions are or the programs is move tmode comma hash 10h. That means the 10h value is loaded into the tmode register. Okay, after loading 10h value we get the timer 1 in mode 1. Okay, then move TL1 comma hash 1ah. That means now the TL has the value 1a and this value calculated previously. The next step is move th1 comma hash 0ffh. Now the th has the value ffh. Okay, then set bit tr1. That means now the tr1 bit is 1 and hence it starts the timer. The next is jnb tf1 to l2. That means jump if tf1 is not set to l2. Whenever the tf1 sets, then clear tr1. That means now tr1 is equal to 0. That means stop the timer. When the timer stops, then complement p2.2. That means whatever the p2.2 has the value, that means if it has the value 0, then make it 1, or if it has the value 1, then make it 0. Okay, that means by complementing we get the square wave of 50% duty cycle. Then clear tf1. That means here tf1 sets. That means when this timer overflows, the tf1 flag sets and we have to clear it. That means here we get tf1 equal to 0. Then again short jump to l1. This process continues and we get a square wave of 50% duty cycle. I hope you all understand this program. Now let's see some C programs here. For example, write a C program to toggle only bit P1.5 continuously every 50 milliseconds. That means now we have to write a C program for the toggle bit P1.5. Toggle means generation of square wave. Similarly, we can also say that toggling means converting zeros to 1 and ones to 0. That means we get here a square wave like structure. Okay, then here we have to use the timer 0 mode 1 to create the delay using 8089C51. Okay, here we only consider the 8051 microcontroller. Okay, that means we have to toggle a bit of P1.5 continuously. The delay is 50 millisecond and we have to use the timer 0 and mode 1. We know that for timer 0 and mode 1 we have to give the values to tmode register 01. Okay, we have already seen this value in the previous video lecture. Okay, now we have to find the values of TL and TH for the 50 millisecond delay. 50 millisecond delay. Let's find first the values of TL and TH. For that purpose, let's consider here the delay is 50 millisecond. Okay, and the crystal frequency is XTAL is equal to 11.0592 megahertz. Okay, we know that the clock period for the frequency 11.0592 is the 1.085 microsecond. We have done this calculation already. Hence, now here we have the delay 50 millisecond. That means 50 millisecond should divided by the oscillator clock period 1.085 microsecond. Millisecond means 10 raised to minus 3 and microsecond means 10 raised to minus 6. This calculation gives us the value 46.082 into 10 raised to minus 3, plus 10 raised to plus 3, and it gives us 46,082 plus 1. That means we get here the value 46,083 clock pulses. Okay, we get the clock pulses 46,083. Let's see once again. Here we get the value of clock pulses as 46,083. Okay, now we have to subtract this value from the maximum value of the timer. That means f. This is the hexadecimal value. We have to convert it into the decimal value. That means 65,536 minus 46,083, and this subtraction gives us the value 19,453. Okay, this is the decimal value, and we have to convert this value into equivalent hexadecimal value. Okay, by equivalent hexadecimal value, how we convert this decimal number into hexadecimal number? This is already learned in the first year. Let's see once again. By using this method, that means we have to convert 19,453 divided by 16. This subtraction gives us, that means 19,453 divided by 16. The quotient is 1, and here the remainder is 3. Now the next quotient is 2. 16 into 2 is 32. We get the remainder here 2, and the next bit is 5. The quotient is 1. That means 16. We get here 9, and the next bit is 3. We get the quotient as 5. Hence we get here 93 minus 80, the quotient as 13. Hence we get here the remainder as 13 and quotient as 1215. Again we have to divide it by 16. We get here the quotient as 75 and the remainder as 15. Again we have to divide by 16. We get the quotient as 16 into 4 is 64, and we get the remainder 11. Again we have to divide this 4 by 16. We get the quotient as 0 and the remainder as 4. Hence we get the code here 4, 11, 15, 13, but we get the code 4. 11 means we get here B, 15 means we get here F, and 13 means we get here D. Okay, I hope you all understand this conversion. That means we get the hexadecimal number 4BFD. Okay, we get the decimal number hexadecimal number 4BFD. Okay, out of which the 4B is loaded into the TH value and FD is should be loaded into TL value. I hope you all understand this calculation. Now let's see the program here. Okay, here is, let's start the program. First of all, write the header file #include register 51.h void t0m1 delay void. This is the delay subroutine. That means timer 0 mode 1 delay. Okay, you can give any name for this The next is S bit, my bit is equal to P1.5. Okay. Then void main void opening brackets while 1, that means repeat forever, again in loop opening bracket, my bit is equal to complement of my bit, that means it toggles the P1.5 bit. Then it calls the delay subroutine T0 M1 delay, timer 0 mode 1 delay, that means it jumps to now this subroutine, and in this subroutine we have to load the values of t mode. We know that we have to assign the value for t mode as 0 1 because we have to operate the timer 0 in mode 1. For that purpose we load the value 0 1. Then the next is load the values of TL and TH. The value of TL is FD. We have calculated this value. The value of TL, the value of TL is FD. Okay. And the value of TH is 4B. Okay. The value of TH is 4B. Then first step is load the T-mode register, load the values in TH and TL. The next is start the timer by setting TR bit, that means turn on timer 0. Then while F0 equal to 0, wait for TF0 to rolls over. Then if TF0 is rolls over, that means TF0 flag sets, then TR0 is equal to 0, that means turn off T0, and TF0 is equal to 0, that means clear the timer flag 0. Okay, I hope you all understand the program here. Now let's see the next program here. Write an 8051C program to toggle all the bits of P2 continuously every 500 millisecond. Use timer 1 mode 1 to create the delay. That means we have to generate here delay of 50 millisecond. Okay, for the toggling of bit or the toggling of all the bits of P2, and we have to use the timer 1 mode 1. Okay, for timer 1 mode 1 we have to load the value 10H into the T mode register. Okay, now we have to find the values of TH and TL. Okay, for that purpose let's see the calculation first. Here is the delay is 500 millisecond, and the crystal oscillator frequency is, that means XTAL, is equal to 11.0592, and for that purpose we know that its period is, that means the clock period is 1.085 microsecond. Then we have to generate the 500 millisecond delay. First of all, how we generate this delay? Let's consider here if we generate the 25 millisecond delay and multiply by its 2, then we get 500 millisecond delay. Okay, for that purpose first of all we have to find the clock pulses for the 25 millisecond delay. Okay, that means here now we want to generate the values for the delay 25 millisecond. For that purpose we have to divide this 25 millisecond divided by this oscillator period 1.085 microsecond. Millisecond means 10 raised to minus 3, microsecond means 10 raised to minus 6. This calculation gives us the value 23,041. After plus 1 we get the value 23,042. These are the clock pulses. Okay, these are the clock pulses. Now we have to subtract these clock pulses from the value F. This is the hexadecimal value, and we have to convert it into decimal. Its decimal is 65,536 minus we get the value 23,042. After subtracting this, we get here 42,494. These are the clock pulses. Okay, these are the clock pulses. Now we have to convert it into the hexadecimal value, and its hexadecimal value is A5FE. A5FE, its hexadecimal value. That means we have to load FE into TL and A5 into TH. Okay, that means we have to load A5FE FE into TL and A5 into TH. Okay, now let's start our program. Here hash include register 51.h, that means header file. Next one is void t1 m1 delay, void main void, opening brackets, unsigned character x, p2 equal to 0 cross 55. That means now p2 assign the value 0 cross 55 means 0101 0101. Okay, then while 1, that means repeat forever, p2 is equal to complement of p2. Here we get the complement of the p2 as 1010 1010. Okay, then for x equal to 0, x less than 20, that means here we get the 20 times value of the x. That means we get here total delay 25 into 20 is equal to 500. I hope you all understand these calculations. Okay, then tm1 m1 delay, closing bracket. Then let's start the delay subroutine. First of all, load the tmode register with the value 10 to obtain the timer 1 in mode 1. Okay, then next load the tl1 value with fe and load the th1 value with a5. These values are calculated depending upon the calculations. Okay, now start the timer by setting the tr1 bit. Then while tf equal to 0, then now monitor the tf1 flag. If tf1 flag sets, then stop the timer tr1 equal to 0 and clear the tf1 flag. Okay, then this execution repeats. I hope you all understand the program here. Now let's see the next program. Write an 8051C program to create a frequency of 250 Hz on P2.5. Use timer 1 mode 2 to create the delay. Here the frequency is given, which is f is equal to 2500 Hz. We have to find the period for it. Then for that purpose we write here 1 upon f is equal to 1 upon 2500. We get here the period as 400 microsecond. This is the period for the entire square wave. That means this is the period for on time and off time. Okay, we have to obtain the period for only on time or only off time. For that purpose divide this 400 by 2. We get the period as 200 microsecond. Okay, and we know that for the crystal frequency 11.0592 megahertz, its period is 1.085 microsecond. Okay, hence to obtain the total number of clock pulses, we have to divide this 200 microsecond with 1.085 microsecond. We get the calculation here 184. Okay, here we get the calculation 184. Remember here that here we use the timer mode 2. The timer mode 2 is the auto reload mode timer, and in this timer the maximum count value is ff, only ff. Okay, I hope you all understand this concept. Now let's see the program. Hash include register 51.h void tmem2 delay void s bit my bit equal to p2.5 void main void opening bracket unsigned character x while 1, that means repeat forever, opening bracket my bit is equal to complement of my bit, that means toggle p2.5 tm1 m2 delay. After this, jump to this delay subroutine. Here the t mode is reloaded with the value t0, that means we use the timer 1 in mode 2. Okay, I hope you all know how this value is calculated. This explanation is already given in the previous video. Then next, the value loaded into th is 184, which is calculated previously here. Okay, now next is set the tr1 bit. Then while tf1 equal to 0, that means while tf1 is set, that means timer overflows, then turn off the timer by tr1 equal to 0 and clear the timer flag tf1 equal to 0. Then here is the closing bracket. This is the very simple program is for the generation of square wave on the pin. Now let's see the another example here. Write an 8051 C program to toggle only pin P1.3 continuously every 250 millisecond. Use timer 0 mode 2 auto reload to create the delay. All the things are similar except the values loaded into the T mode register. Now we have to use timer 0 in mode 2, hence we have to give the value 0 to H for the T mode register. Okay, then we have to load the th0 register here. Here is a printing mistake. Here is load th0, that means th0 loaded with the 23 value, and this 23 value is depending upon the calculation. Okay, I hope now you are able to do the calculation for this 23. Okay, the remaining program is same. Okay, except the values of t mode and th0. Make correction here, this is the th0. I hope you all understand. Now let's see the next program. Write the C program to generate a square wave on p2.2 having 2500 Hz frequency and 70% duty cycle. Consider XTAL equal to 12 MHz. Here the frequency is given 2500, hence we have to find period for it, that means t is equal to 1 upon f and is equal to 1 upon 2500, which gives us the period of 400 microsecond. For given duty cycle 70%, we can obtain the duty cycle from the formula T on upon T total. That means the T total is T on plus T off. That means we get the duty cycle formula as T on upon T on plus T off. Putting the values, duty cycle is 70%, T on is here, and the T total is 400 microsecond as calculated. After this calculation, we get the values for T on as 280 microsecond. Okay, from T on we can calculate T off as 400 minus 280, because here we know that T total is equal to T on plus T off. Now we know the value of T total and T on, then we can find the value of T off such as T total minus T on. Okay, I hope you all understand the calculations here. Here the value of T on is 280 microsecond and value of T off is 120 microsecond. Hence we have to find the values for 280 and 120 separately. The clock frequency is 1 divided by 12 into crystal frequency, that means 1 divided by 12 into 12 megahertz, means here is 12 megahertz, means 12 into 10 raised to 6. This calculation gives us the period 1 microsecond, and this calculation is already done in previous video. Okay, now let's see the number of clock pulses required for t on, that means for 280 microsecond hour. We can obtain this by dividing 280 microsecond by 1 microsecond. We get the value 280 clock pulses. Okay, then we have to find the values for th1 and tl1 by subtracting this value 280 plus 1 from the 65,536. Okay, we get the value 65,256, and we have to convert it into the hexadecimal. Its hexadecimal value is FE8, where TH1 has the value 0FE and TL1 has the value 0E8. Okay, I hope now you are familiar with how to calculate these values. Similarly, we can calculate the values for 120 microsecond, and the values for the 120 microsecond are th1 equal to 0ff and tl1 equal to 088. Okay, now load the tmod register with the value 10h to obtain the timer 1 mode 0. Okay, here the program is given. In this program we can see here that the first is hash include register 51.h, next bit s bit is equal to f1 p2.3, void on and void off. These are the two subroutines now. Then void main void opening bracket while 1 repeat forever, f1 is equal to 1, then give the delay of t on. That means now we jump to this t on delay. That means whatever this subroutine has the delay is executed after this delay, then make f1 equal to 0, that means complement it, and then jump to the t of delay. Okay, I hope you all understand the basic procedure here. The delay subroutine for t on is tmod is equal to 10, that means load the values in tmod register to obtain the timer 0 in mode 1, the timer 1 in mode 0. I hope you all understand. Then load tl1 equal to 8e, th1 equal to ef, and then start the timer by setting the tr1 bit. Monitor the tf1 flag. If tf1 equal to 0, then stop the timer by tr1 equal to 0, and then clear the tf1 flag. Okay, then similarly we can give the subroutine for the t off. All the procedure is same except the values in th and tl. In t on we give the value for tl1 is 8e, here we give the value 88. In t on we give the value of th as ef, here we give ff. I hope you all understand the programs related with the timer mode 1 and mode 2. Thank you.